Hello there, and welcome to the Sleepy Science Channel. I'm so glad you're here. Maybe you've had a long day, or maybe you're just the sort of person who likes to fall asleep thinking about stars and gravity instead of sheep. Either way, tonight's journey is for you. You don't need to do anything but rest. Let your thoughts soften, your breathing slow, and your mind uncoil like a ribbon floating in the dark. Tonight, we're going to travel back to a moment that lies at the very edge of what science can see. The beginning of the universe. Or, at least, the earliest thing we can point to and call a beginning. It's a story not just of matter and light and time, but of the limits of what it means to know something, of what it means for a moment to even exist. Don't worry, we won't get too far ahead of ourselves. We'll go slowly, gently, thoughtfully, and just before we begin, if you find comfort in these quiet journeys through time and space, if they help you drift off or simply soothe your mind after a long day, consider gently tapping the like button. It helps others find their way here too, one sleepy soul at a time. Now let's begin. Not with a bang just yet, but with a question. One that sits quietly beneath almost every other. A question that hides in the corners of astronomy, physics, and cosmology. Where did everything come from? It's the kind of question that feels too big to hold. Bigger than stars or galaxies. Bigger than thought itself. And for a long time, science didn't try to answer it. After all, how do you measure the beginning of time when time is the very thing that's beginning? How do you explain the birth of space when your only tools for explanation rely on space already being there? But that silence didn't last forever. In the early 20th century, something shifted. Not because someone found the answer, but because new clues began to appear. Observations, data, dots on graphs, strange fingerprints in the night sky. And slowly, a pattern emerged, a quiet but unmistakable suggestion that the universe itself is not static. It's expanding. The space between galaxies is growing, not because they're flying away from each other like debris, but because space itself is stretching, everywhere, all at once. The idea of a changing universe was, at first, uncomfortable. For centuries, people had assumed the cosmos was eternal and unchanging. Even Einstein, when first faced with the implications of his own equations, introduced a cosmological constant to cancel out the possibility of expansion. Not because the math required it, but because the idea of a dynamic universe seemed too strange, too unstable. He would later call that adjustment his greatest mistake. But as more observations came in, the evidence became harder to ignore. In the 1920, the astronomer Edwin Hubble made a discovery that transformed our understanding of the cosmos. When he studied the light coming from distant galaxies, he noticed something unexpected. Their light was stretched, reddened, as if being pulled away. And the farther away the galaxy was, the more stretched its light appeared to be. It wasn't just that some galaxies were receding, all of them were. And the farther they were, the faster they seemed to be moving. This pattern could only mean one thing. The universe was expanding. Not with galaxies flying through empty space, but with space itself growing, slowly carrying the galaxies apart like raisins in a rising loaf of bread. It was a radical idea, but the data supported it. And if the universe is expanding today, then that means, in the past, it must have been smaller, denser, hotter, wound tighter and tighter into some earlier state. The further back you go, the more extreme things become. Eventually, this reasoning led scientists to a remarkable conclusion. If everything is spreading apart now, and if that pattern continues as you rewind the clock, then the universe must have once been compacted into an incredibly hot, incredibly dense state. A state where all the matter, energy, space, and even time itself may have been compressed together, not into a single point exactly, but into a state so extreme that our current physics begins to break down. This became the foundation for what we now call the Big Bang Theory, a somewhat misleading name since it wasn't really a bang at all. There was no explosion in space because space itself was what was beginning. There was no sound, no light in the way we normally imagine it. Just an unfolding of everything, everywhere, all at once. A moment when the universe didn't expand into space, but created space as it expanded. It's important to pause here, because this is where science meets its current horizon. The Big Bang Theory doesn't actually describe the very beginning. It describes everything that happened after the universe began expanding. It gives us a framework to understand how the cosmos evolved, from that early fireball to the cool, structured universe we see today. But the actual moment of beginning, the exact nature of time, space, and cause before that expansion remains cloaked in mystery. We don't yet know what, if anything, came before. We might never know. Let's look more closely at what we can actually say about the Big Bang, not as an abstract idea, but as a series of physical events. We don't begin with a singularity in the classic sense, at least not in the way it's often described in popular science. A true singularity implies a point of infinite density, infinite temperature, infinite curvature of space. And while general relativity points in that direction, quantum mechanics does not tolerate infinities so easily. What we're really dealing with is a frontier, a point beyond which our current understanding breaks down, not because there's nothing there, but because our math no longer works. What we do know is this: the earliest moment we can meaningfully describe is called the Planck epoch. This is the first tiny sliver of time after the universe began expanding, just 100 million trillion trillionths of a second after the beginning. That number is almost beyond imagining. If you stretched the entire history of the universe across the width of your room, this moment would be smaller than a single grain of dust. It's a scale where gravity, quantum physics, and space-time itself are all tangled together in ways we don't yet understand. During the Planck epoch, the universe was unimaginably small and incredibly hot. All four of the fundamental forces we know today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are thought to have been unified into a single force. Not just acting together, but actually indistinguishable from one another. A single superforce, embedded in a quantum froth of rapidly fluctuating energy and curved spacetime. But we don't have a full theory that can describe this state. That's one of the greatest goals of modern physics, to create a theory of quantum gravity, something that can blend Einstein's general relativity with quantum mechanics into a unified description of nature at its most extreme. Until then, the Planck time remains a horizon. We can't see past it, but we can approach it and describe what likely happened next. As the universe continued to expand, and just as importantly, as it cooled, the forces began to separate. This process is called symmetry breaking. First, gravity split off from the other forces. Then the strong force separated. And as temperatures continued to fall, the electromagnetic and weak nuclear forces parted ways as well. These weren't chaotic events, but smooth transitions, like different phases of matter emerging as a hot liquid cools into a crystal. With each step, the universe became more structured, more differentiated, and new possibilities emerged. One of the most dramatic changes came just after these force separations, a moment called cosmic inflation. According to inflation theory, the universe didn't just expand, it ballooned. In a tiny, tiny fraction of a second, space itself expanded faster than the speed of light. Not in violation of relativity, since it wasn't matter moving through space, but space itself stretching. The scale of this growth is staggering. In less time than it takes light to cross a single atom, the entire observable universe may have grown from subatomic size to something large enough to contain galaxies. Why did this happen? We're not entirely sure. But one leading idea is that a high-energy field, called the inflaton field, briefly dominated the energy of the universe. This field triggered exponential expansion, then decayed, dumping its energy into the cosmos and creating a uniform bath of particles and radiation. That event is sometimes called the reheating of the universe, and it marks the start of what we usually think of as the hot Big Bang, the moment when particles, atoms, and light began their long journey toward forming stars and galaxies. After inflation ended, the universe was filled with an incredibly hot, dense plasma, a seething mixture of particles, energy, and radiation. Protons and neutrons began to form from the raw energy and then combined into simple atomic nuclei. This process, called primordial nucleosynthesis, happened just a few minutes after the beginning, and it determined the basic mix of matter in the cosmos. Mostly hydrogen, some helium, and trace amounts of other light elements. It's astonishing how much was decided in those early minutes. The balance between matter and antimatter, the density of the universe, the seeds of structure that would one day become galaxies. Much of it was baked in during this brief, chaotic period, governed by laws we're still trying to fully understand. But one thing is clear. By this point, the universe was no longer just a quantum fluctuation. It was a real place, full of energy and motion and potential. And yet, it was still opaque. Light couldn't travel far because it kept bouncing off charged particles in the dense plasma. The universe glowed, but not with visible light. It would take hundreds of thousands of years before the cosmos cooled enough for electrons to settle into stable orbits around nuclei, forming neutral atoms and allowing light to travel freely. When that happened, the first photons of visible light began to stream through space. That light is still with us today, stretched by billions of years of expansion. We call it the cosmic microwave background, and it's the oldest light we can see. Let's pause now and focus on the faintest light in the sky. A glow that isn't tied to stars or galaxies, but something far older. Something woven into the very fabric of space. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This moment is called recombination, and it marked a dramatic shift in how the cosmos behaved. For the first time, light could travel freely. No longer trapped in a fog of charged particles, photons began to stream across space, in every direction. That light is still traveling today. We call it the cosmic microwave background, or CMB for short. It fills the universe, not in patches or streaks, but as a smooth, nearly uniform bath of radiation, like the afterglow of creation itself. It's not visible to the naked eye, because time and expansion have stretched its wavelengths down into the microwave part of the spectrum. But it's still there, surrounding us like a faint whisper of ancient heat. The discovery of the CMB was, in many ways, an accident. In 1965, two radio engineers, Arno Penzias and Robert Wilson, were working with a sensitive antenna in New Jersey. They weren't searching for relics of the early universe. They were troubleshooting a persistent noise in their instrument, a steady hiss that wouldn't go away, no matter where they pointed the device. They even cleaned out nesting pigeons, suspecting droppings might be to blame. But the signal remained. What they'd stumbled upon, unknowingly, was the cosmic microwave background, the cooled remnant of the universe's earliest light. At nearly the same time, a group of physicists at Princeton had predicted that such a glow should exist. When the two teams connected, it became clear that this was a moment of extraordinary significance. The Big Bang was no longer just a theoretical idea. It had left behind a signature, a map, a direct imprint of the early universe, still visible today. At first glance, the CMB looks astonishingly uniform. No matter where you look in the sky, its temperature is nearly the same, just a few degrees above absolute zero. But when instruments became precise enough, scientists noticed something remarkable. The smooth glow wasn't perfectly smooth. It had tiny ripples in temperature, fluctuations just millionths of a degree in size. Barely detectable, but incredibly significant. These fluctuations are called anisotropies, and they represent tiny differences in the density of the early universe. In some places, matter was packed just a little more tightly in others, a little more loosely. Over billions of years, gravity would amplify those tiny differences, pulling matter together to form galaxies, stars, and eventually planets. Without those ripples, there would be no structure at all. No galaxies, no stars, no life. Just a featureless sea of light and gas. The CMB is, in that sense, a kind of baby picture. A snapshot of the universe when it was just 380,000 years old, long before the first star, long before Earth. And by studying the shape and scale of those ripples, cosmologists can reverse engineer the ingredients of the cosmos. They can measure how much of the universe is made of matter, how much is dark matter, and even how much is something stranger still, dark energy, a mysterious force that affects the universe's expansion over time. One of the most important missions to map the CMB in detail was the Planck satellite, launched by the European Space Agency in 2009. Over several years, it produced the most precise image we've ever had of the early universe, a glowing oval of subtle color shifts, each one marking a tiny difference in temperature and density across the sky. From that data, we've learned that the universe is about 13.8 billion years old. We've learned how fast it's expanding. And we've confirmed that only about 5% of the universe is made of ordinary matter, the kind that makes up stars, planets, and people. The rest appears to be invisible, dark matter, which pulls on galaxies through gravity, and dark energy, which pushes the universe apart. And yet, even with all that insight, the CMB also marks the limit of what we can see. Not because there's nothing beyond it, but because it's the farthest light that's ever reached us. Anything earlier than recombination is still hidden behind a veil of glowing plasma. To see further back, we'd need something other than light, something even older. And that leads us toward the next great mystery. Not what we can see, but what we can only infer. Let's return to the earliest moments after the Big Bang, not to the expansion itself, but to what it left behind. Energy, heat, and, eventually, matter. One of the most profound questions in cosmology is deceptively simple. Why is there something, rather than nothing? The laws of physics, as we understand them, suggest that matter and antimatter should have been created in equal amounts. For every proton, an antiproton. For every electron, a positron. And when these opposite particles meet, they annihilate, returning to pure energy. In theory, the early universe should have been symmetrical. And yet, it wasn't. When we look around today, we see a universe made almost entirely of matter. Antimatter is rare, and mostly produced in particle accelerators or high-energy cosmic events. Somehow, in those first fractions of the second, matter gained the upper hand. Not by much, perhaps one extra particle of matter for every billion pairs, but enough that, when all the annihilations were done, that tiny excess was left behind. And from that small remainder came everything. This imbalance, the triumph of matter over antimatter, is called Baryon asymmetry. And to this day, it remains one of the most intriguing open questions in physics. What tipped the scales? Why did matter come out ever so slightly ahead? Physicists have proposed several mechanisms that might explain it. One possibility is that the laws of physics themselves aren't perfectly symmetrical. There are processes, subtle ones, that may treat matter and antimatter just a little differently. These are called CP violations, short for charge parity violations. They've been observed in certain particle decays, but not yet in a way that fully explains the imbalance we see. Another idea involves particles that no longer exist, heavy, exotic forms of matter that may have decayed in asymmetric ways during the earliest moments of the universe. These decays could have favored matter over antimatter in just the right amounts, setting the stage for everything to come. But these particles are purely theoretical. If they ever existed, they vanished almost instantly, leaving only their influence behind. Whatever the mechanism, the result was profound. That slight excess of matter, perhaps just one part in a billion, would go on to form every atom, every molecule, every star. Without it, there would be no galaxies, no light, no chemistry, no life. The entire visible universe is built on what might be described as a cosmic rounding error, a delicate imbalance written into the fabric of creation. And what's even more humbling is this: we don't know why it happened. Not fully. We can describe it. We can measure it. But the underlying cause remains out of reach. It's as if the universe left us a clue, but not the key. And so, scientists continue to search, in particle accelerators, in neutrino experiments, in the faint echoes of ancient radiation, for any sign of how the laws of physics might favor matter just enough. This search isn't just academic. It touches the deepest philosophical questions we can ask. Why is there something rather than nothing? Why do the laws of nature permit a world like ours to emerge from such a delicate beginning? These are not easy questions. But science, moving gently, step by step, can sometimes circle closer to the heart of them. In the end, what we call the universe, the stars, the galaxies, the swirling arms of the Milky Way, and the atoms in your fingertips, all come from that leftover sliver. That tiny imbalance that the early universe didn't quite erase. And from there, structure began to emerge. Gravity took hold. The densest regions of matter began to collapse, drawing in more material, heating, compressing. These would become the first stars, not yet formed, but already destined. The universe, once smooth, was beginning to ripple, to clump, to become uneven in ways that mattered. But before stars could shine, before galaxies could spiral, and long before planets could take shape, the universe had to pass through a long, quiet phase, one without light, without structure, and almost without name. A time that cosmologists now call the Cosmic Dark Ages. That is where we'll go next. The universe had light once, that early glowing fog of photons released when atoms first formed. But that light faded, stretched by expansion, thinned by distance, cooled by time. And what followed was a kind of stillness, a darkness, a long cosmic night. This era is called the Cosmic Dark Ages, and it lasted for hundreds of millions of years. During this time, the universe was still full of matter. Hydrogen and helium atoms drifted quietly through expanding space, slowly gathering into ever denser clumps under the pull of gravity. But there were no stars to ignite, no galaxies to illuminate the sky. The photons from the Big Bang still existed, but they were no longer visible, and no new ones had yet been born. If you could have stood in the middle of space during this period, you would have seen nothing at all. No starlight, no planets, no movement beyond the slow gravitational collapse of vast hydrogen clouds. The universe was vast and utterly dark, yet quietly preparing for something astonishing. Over time, millions upon millions of years, gravity continued its patient work. The denser regions pulled in more gas. Tiny fluctuations in density, seeded back in the earliest instants, began to grow. These clouds of hydrogen collapsed slowly, deepening into knots of pressure and heat. And at a certain threshold, one we know well from studying stars today, fusion began. The first stars flickered into being. They were likely much larger than most stars we see today, perhaps hundreds of times the mass of our Sun. These were the population, the third stars, the first generation, born from pure hydrogen and helium, untouched by heavier elements. They lived fast and died young, burning brightly and collapsing quickly into black holes or massive supernova. Their light marked the end of the cosmic dark ages, not all at once, but gradually. As these early stars ignited, they poured ultraviolet radiation into their surroundings, stripping electrons from nearby hydrogen atoms and turning cold neutral gas back into an ionized plasma. This process is called reionization, and it slowly peeled back the veil of darkness across the cosmos. Reionization didn't happen overnight. It was a gradual process, spreading unevenly across space. The first stars formed in clusters, tiny, primitive galaxies, and their radiation carved glowing bubbles around them, clearing pockets of transparency in the dark. Over hundreds of millions of years, these bubbles grew and merged, until the fog of neutral hydrogen was mostly gone. Space became visible again. This phase of the universe, from the ignition of the first stars to the completion of reionization, is incredibly difficult to observe directly. Light from those early stars is faint, distant, and stretched across billions of light years. But new telescopes, like the James Webb Space Telescope, are beginning to glimpse galaxies that formed just a few 100 million years after the Big Bang, offering our first direct look into that long-lost era. These early galaxies were smaller, denser, and more chaotic than those we see today. But they were real, cradles of stars powered by gravity and fusion. With them came the first complex chemistry, the first heavy elements, the building blocks of everything that would come later: planets, oceans, carbon, life. When the first stars died, they did not vanish quietly. Many of them exploded in brilliant supernova, scattering newly forged elements across space: carbon, oxygen, iron, and more. These materials seeded the next generation of stars. And around some of those stars, small disks of dust and gas began to form, swirling, colliding, slowly shaping themselves into planets. Galaxies began to assemble into larger structures. They collided, merged, and spun into elegant spirals and elliptical forms. The cosmic web, a vast filamentary network of dark matter and galaxies, began to emerge. The universe was no longer smooth and dark. It was alive with light, complexity, and motion. By around 1 billion years after the Big Bang, the universe had entered a new era, one that looked, in broad strokes, much like the cosmos we see today. Still evolving, still expanding, but lit now by stars and shaped by gravity. The long silence was over, and the symphony had begun. By the time the universe was a few billion years old, it had begun to look familiar, at least from a great distance. Galaxies had formed, glowing with stars and threaded together by gravity into vast structures. Some spun into elegant spirals. Others clustered into tight knots. Great voids stretched between them like bubbles in a cosmic foam. The universe, once uniform, had become richly textured. And yet, it was still expanding. That part never stopped. Ever since the Big Bang, space itself had been stretching. And as galaxies moved apart with the flow of this expansion, the light they emitted was stretched too, shifted toward longer, redder wavelengths. This phenomenon is known as cosmic redshift, and it provides one of our clearest windows into the scale and speed of the universe's growth. The more distant a galaxy is, the more its light has been stretched, and the faster it appears to be receding. This idea that the universe is expanding was first confirmed in the 1920s, thanks to the work of Edwin Hubble. By measuring the redshift of distant galaxies, he discovered a clear pattern. The farther away a galaxy was, the faster it appeared to be moving away. It was as if space itself was stretching in every direction. For decades, scientists assumed that this expansion must be slowing down. After all, gravity pulls things together, and with so much matter in the universe, wouldn't that eventually halt the growth? Some even imagined a big crunch, where the cosmos might one day collapse back into itself. But then, in the late 1990s, something unexpected was discovered. Two independent teams of astronomers were studying distant supernovae, brilliant explosions that serve as standard candles, allowing us to measure vast cosmic distances. What they found shocked the scientific world. The expansion of the universe wasn't slowing down, it was speeding up. Some force or property of space, was causing the universe to expand faster over time. That force has been given a quiet, mysterious name: dark energy. Dark energy is not a substance we can see or touch. It doesn't glow, it doesn't clump, and it doesn't behave like matter. Instead, it seems to be an intrinsic property of space itself, a kind of energy woven into the vacuum, gently pushing everything apart. Today, dark energy makes up roughly 70% of the universe. It's the dominant force in cosmic evolution, yet remains almost entirely unexplained. We don't know if it will stay constant, or if it might change over time. We don't know what causes it, whether it's a true cosmological constant, as Einstein once proposed, or something more dynamic, like a slowly evolving field. What we do know is that its effects are profound. Over time, galaxies not bound together by gravity will drift farther and farther apart. Eventually, distant galaxies will slip beyond the horizon of visibility, not because they're moving through space, but because space itself is expanding so quickly that their light will never reach us. In the far future, the universe may become a colder, lonelier place. The stars will still shine for a time, but beyond a certain point, only the closest galaxies will remain visible. The cosmos, once bright and buzzing with activity, will fade into quiet isolation. And yet, even in that future silence, the universe will continue to evolve. Stars will age and die. Some will collapse into white dwarfs, neutron stars, or black holes. Others will be born from the scattered ashes of earlier generations. But over vast timescales, trillions of years, star formation will slow. The fuel will run low. Fewer stars will be born, and the galaxies will grow dim. One by one, the lights will go out, and the universe will pass into what some call the degenerate era, a time dominated not by stars, but by remnants. White dwarfs drifting quietly, black holes swallowing slowly, time itself stretching on without end. Eventually, even the black holes may vanish, evaporating over eons through a process called Hawking radiation. And if dark energy continues to accelerate the expansion, the universe may thin and cool until it approaches absolute stillness. No stars, no warmth, just particles and space. But that too is only one possibility. The future is vast and full of quiet questions. The universe is not static. It never has been. From the moment of the Big Bang, it has grown and changed. Particles formed. Light escaped. Galaxies spun into being. Stars lived and died. And even now, billions of years later, everything is still in motion, still unfolding. But what lies ahead? If dark energy remains constant, if the force accelerating the expansion of space continues just as it is today, then the universe will become colder and darker over time. This outcome is sometimes called the Big Freeze, a future where expansion never stops, and where, eventually, the stars burn out, the black holes vanish, and all that's left is a thin, silent fog of particles. It's not a dramatic ending. No crash, no fire. Just a long, slow exhale into stillness. But the Big Freeze isn't the only theory. Some physicists have imagined a different ending, one where dark energy doesn't remain constant, but grows stronger over time. In this scenario, the acceleration of the universe would increase, slowly tearing galaxies apart, then stars, then planets, and eventually even atoms. This idea is called the Big Rip. It wouldn't happen suddenly. It would unfold over billions of years. But in the final moments, space itself could become unstable, stretching so fast that nothing could remain bound. Even the tiniest building blocks of matter might be pulled apart. It's a more dramatic vision, and still speculative, but one that follows logically from a dark energy that changes with time. Then again, perhaps the expansion won't go on forever. Some cosmological models suggest that dark energy might reverse, that the universe, after reaching a certain point, might slow down and collapse inward, a reversal of the Big Bang, known as the Big Crunch. Everything drawn back together, heat rising, density increasing, until perhaps another explosion begins the cycle anew. From this, some have proposed a universe that oscillates, a cyclic cosmos, forever expanding and contracting, like breath. The idea of a cyclic universe is ancient, whispered in myths long before science gave it form. A cosmos with no true beginning or end, only transitions. Deaths that lead to births. Collapses that spark new expansions. A universe that breathes in epochs. Modern physics doesn't rule it out. Some theories, like loop quantum cosmology, suggest that the Big Bang may not have been the absolute beginning, but a rebound, the result of a previous universe collapsing under its own weight. Others imagine more complex geometries, multiverses, where our universe is one bubble among many, or quantum fluctuations, spawning new regions of space beyond our cosmic horizon. We don't yet know if these ideas are testable. They remain, for now, at the edge of speculation. But they emerge from real mathematics, real physics, and they offer something deeply human, a sense that the story may not be over. that the cosmos may contain more chapters than we can yet imagine. And yet, even if the future is unknowable, the present is not. We are here, in this brief moment of light, between the darkness before and the silence to come. The future of the universe stretches far beyond our lifetimes, beyond stars, beyond galaxies. It's a canvas of unimaginable time, painted not with brushstrokes, but with motion, temperature, and space itself. And while we may never witness its distant fate, we are part of its present. A momentary ripple in a sea of change. Living on a planet warmed by a star, orbiting within a galaxy, drifting through a universe that began in heat and ends in silence. The same laws that govern the life of atoms shape the fates of stars. The same forces that bent the early universe now guide its future. To study the cosmos is not just to look outward, but to see ourselves differently, as part of something vast, ancient, and ongoing. We are not separate from the universe's story. We are a brief line in its unfolding poem. And so we followed the thread from the first spark of time through the silence and the stars to the far horizon of what may yet come. We've spoken of particles smaller than sight and distances that light takes billions of years to cross. We've wandered through darkness, not as something to fear, but as the space from which all things emerge. If you're still awake now, perhaps you're resting quietly, letting the shapes of galaxies settle behind your eyes. Or perhaps you've drifted off already, floating somewhere between memory and dream, carried by waves of starlight and quiet curiosity. Wherever you are in this moment, thank you for being part of this quiet journey. If this journey helped ease your thoughts, if it brought comfort or wonder or rest, consider gently tapping the like button and subscribing to the Sleepy Science channel. It helps others find their way here too, one sleepy soul at a time. And now, as you rest beneath the quiet stars, as galaxies turn in the darkness beyond, and ancient photons whisper across the sky, just remember, the universe is still unfolding, still drifting, still singing softly in the language of time. And so, under the deep, dark silence of space, the story continues.